Hello, everyone. Thank you for introduction. And I'd like to talk my current study, whose title is Deep Neural Networks Predict Emotion Responses Using Whole Brain Neural Activity. So in recent fMRI studies for emotion decoding, some multiple voxel pattern analysis based on supportive vector machine has been widely used. To conduct this analysis from using fMRI data from multiple subjects, group level analysis is conducted to identify certain otherwise region of interest. And neural information from these otherwise and are used as an input for SVMs to classify the two classes, such as happy or sad. However, this kind of approach is limited due to ROI-based analysis needs some statistical threshold. And also, as we all know, the emotional processing from the human is based on a combination of neural activation of the whole brain. And in addition, binary classification only identify two emotion states. It is limited to take account of the emotional state level, so yeah, it is maybe important for better understanding our complex emotion states. So therefore, a research challenge question is that it is possible to predict subject emotion responses using whole brain fMRI data in individual level. Maybe it is possible for SVM, but I assume that it will be challenging for SVM because such fMRI data has large dimensionality that are confounded by complex and subtle neural activation of the whole brain. So we were motivated to use deep neural networks. Because it has been demonstrate the capacity to find the efficient feature representation that are hierarchically organized from the complex input patterns. For instance, when we look at the trained DNA models, and it represents simple features to complex feature map from low to higher layer. So the aim of this study is to validate the feasibility of DNNs for emotion decoding using the whole brain neural activation in individual level. So this is our task paradigms. We recruited 10 healthy subjects, and each subject listens 80 affective sounds, and they select the mannequins that best represent their emotions using 3 emotion categories, such as arousal, dominance, valiance. And each emotion category has 9 points scale, 1 to 9. And for instance, in the valiance, 1 is the very unhappy, 9 is the very happy. In order to predict emotion responses using the whole brain, this is our adapted DNA models with 3 hidden layers and explicit control weight sparsity scheme. Weight mean here these weight parameters that are fully connected across node between consecutive layers. And sparsity level of these weight parameters were explicitly controlled for each hidden layers via L1 regularization parameters. And neuronal activation from sound base are used as an input for the DNN and to predict each of emotion level, let's say, level. And this is a result, and from the individual subject, and predict the emotion response from DNN, and were highly correlated with the related emotion from subject. However, there are little change in predict emotion response in the SVM, and that demonstrates the inability to predict related emotion responses in the SVM. So based on this result, we estimate the correlation coefficient as a performance index, and in the group level, of course, as we can expect, there is superior performance from the DNN to SBM models. Sorry, I forgot to mention about we try to compare the prediction performance of the DNN with the support vector machine with the linear or nonlinear, and those models has been systematically compared under a nested bifold cross validation. Yeah. And also investigating how DNN learn is very important because we would like to know the interpretations, how the DNN learn feature map that are from the input patterns without any knowledge. And one of the way is that we can just simply approximate feature map by multiplying the weight parameters across layer. And then the final stage we can have just frame map. Let's say the 1 by 55,000 voxel we have. And let's look at the hierarchical feature representation map. So first, I just look at the first hidden layer and first node. It represents a high positive and negative intensity in the insular area. And also second node represents the negative intensity in the auditory area. And those, this one is a correlation matrix across nodes. And those are uncorrelated. When I look at further deeper, and those maps represent a mixture patterns from the first level, and also the correlation becomes higher across nodes. And also at the final stage, we can have the brain map. I call this output feature map, and each map. So as you can see, the high positive, negative intensity in the area highly associated with the emotion state, let's say insula or midfrontal cortex area, so on. And these estimated output feature maps were used as those maps we can estimate in individual and each emotion category, and those maps were subject to group level analysis. And this is a group maps regarding the linear multiplication of a wave feature that I mentioned. And overall, there are distinct patterns across 3 emotion categories. In case of variance, we can see there are stringent negative intensity in auditory area, and we can it would have been suppressing the dominant activation in the auditory area evoked from our affective sound. And we can imagine that the correct emotion prediction, very happy or unhappy response is made by efficiently suppressing this auditory sensation and by amplifying the circulatory that are related with the emotion processing. And the other way, we can, actually in this study, we also suggested another way to interpret the weight feature. We call the input pattern estimations by maximize or minimizing emotion response. So once we train the weight parameter, we can just put as an initial weight. And by fixing the values, let's say the 9, which is high emotion response, and then we can train again to estimate the input patterns. And we can just calculate the updated rule by using the cost function from the first derivative of this cost function. And also the input pattern, we can show the map depending on the high or low emotion response. So this is also a group map, and this one is the high arousal, low arousal group map. And this is a high dominance and low dominance, and high variance, low variance. And also, as you can recognize, those two maps, just the different thing is just sign opposite, but slightly different. Let's say at the linear multiplication wave feature shows the mixture of medial orbitofrontal cortex and ACC area. But in this case, when subject become happy, feel happy, let's say this medial orbitofrontal cortex is showed some high positive intensity, but in this case is negative intensity, including the ACC area, and so on. And conclusion, actually, as far as I'm aware of, this is the first study and that applied the DNN to predict the emotion response using whole brain. And yeah, of course, we show that the superior prediction performance of DNN to SBM models. And also, we didn't put any prior knowledge, just to train. And we look at the training feature, but it represent the neural nets, including the insula and medial orbitofrontal cortex areas, which are highly associated with human emotion processing. And future work, maybe this kind of model we can straightforwardly extend to understand emotion circulatory of patients with neuropsychiatric or neurological disorders. So I'd like to thank my PI, Jong-An Lee, and my collaborator, Peter Bentatinis, and I really appreciate both their constructive and valuable comments. And also, I'd like to thank you, my member. And if you are interested or if you want to discuss with me, you can just come and see my poster. It's tomorrow. And also, we provide some Python-based code, including Piano or TensorFlow. So far, we just provide DNN for classification model, but I will upload it, DNN for regression model soon, yes. So, thank you.
Hi, I've read the paper that you group published before,
yes.
And since this is a very small sample size data, and previously the paper your group is doing are applying some weight regularization and
yes.
also applying some probably dropout or batch normalization. Could you explain more about that, how you prevent the overfeeding?
Yeah, so actually the main point is that we try to control the sparsity level, so which is associated with the L1 parameters. And actually, in the literature of the machine learning, I mean the deep neural network field, they use the regulation parameters to prevent overfitting, with the small data. And actually, this one this model that I mentioned has been demonstrate its efficacy in the neural imaging data. Maybe you can just maybe I can simply show the reference. In here, there is some reference. Maybe you can check how it works.
Okay, thank you.
Yeah, thank you.
Maybe we can just, sorry. I'd like to have a round of applause for all of our presenters for today. Thank you very much. And I'd just like to invite a direct conversation with any of our presenters afterwards. Thank you.